be true. So we really don't know, so you err on the side of caution. What's the other really big glaring thing?
You get more radiation from an airplane fire?
You do. You get, that's a fair amount of dose. We'll talk about that in a little bit. How many of you go swimming in the ocean? Okay. Do you drink all the water that you drink in a year drinking ocean water? So that these things that are reporting 20 people, 100 people, they're assuming that you drink, that the entire US population drinks nothing but ocean water for the rest of their lives. Yeah, it's ludicrous. So this is yeah, it's really idiotic. And it's basically said to forward an agenda. So I mean, I'll say you can like nuclear power, you can hate it, but you can make conservative assumptions, but don't make ludicrous assumptions. So it's people with a political agenda. Other accidents like Chernobyl have been much more serious in terms of the greater surrounding population or the continent, but Fukushima was nowhere remotely close to that magnitude. Okay, so yeah, so to sort of reiterate what I already said, so the entire system of global distribution of radionuclides is essentially impossible to model. Knowing what each and every person eats is impossible to model. So in health physics, what's always done is very conservative assumptions are made. We assume linear no threshold is true, even though we know it's all the data points to it's an overestimation of risk. And then you say, well, I don't know how much ocean water you drink. I'll assume that's all that you drink. So very conservative estimates are made in health physics, sometimes too conservative in my opinion. So who do you trust? You can trust experts in the field that don't have a vested interest. So you can trust me, I promise. Fukushima doesn't pay me to come around and say, wasn't that, nothing, it's okay in the US, don't worry about it. So really trust people that don't have a vested interest. So whether you believe in global warming or not, be a little skeptical of the scientist who's wearing, the Chevron, jacket and jumping into his Ferrari afterwards and whatnot. So believe people that don't have a vested interest, and typically that's folks from academia. But believe it or not, research scientists don't get paid a lot of money, and usually they're being pretty honest. So, and a lot of this data from Fukushima is actually was done by folks just like you a number of years ago. So it's mostly folks that went on to graduate school and got their master's and PhD dissertations in measuring these things and doing the models and whatnot. So it doesn't come from suspicious people in smoke-filled rooms. It comes from students, for the most part, graduate students. Okay, background radiation. So a couple of years ago, it's sort of hard to see, a couple of years ago, the US population reached a very interesting point from a philosophical point of view, where the amount of background radiation was less than the amount of anthropogenic or man-made radiation. So you're getting more, as a population averaged, of course, from artificial sources as you get from natural sources of radiation. And I just spent a whole bunch of time saying it's not from nuclear power, it's not from my little reactor down the road. So where is it coming from? What's that? Yeah, it's all medical. It's like 95% medical. So it's getting a single CAT scan. I said your annual limit. So if you come to my reactor for a tour, you'll get about 1 millirem, which is equal to how much you'd get living in Sacramento for a day anyways. So for an hour tour, you get about as much background radiation as you normally would for a day. If you go to Denver, where it's a little bit higher up, they have more granite, more uranium in the granite, it's about 3 or 4 times that. You get a CAT scan, you get 1,500 millirem in however many few minutes it takes to get a CAT scan. If you got 1,500 millirem at my facility, I would be in a lot of trouble. I would be fined by the Nuclear Regulatory Commission. I might lose my job. But if you go to a hospital, it's perfectly fine because they say there's this benefit for you. Whereas getting a tour of my facility, there's a small benefit, but not a medical benefit for doing it. So it's all this medical applications is where it's coming from. It breaks it down. Space exposure, airplanes is considered anthropogenic. This big red one is background, and that's radon. So has anyone heard of radon? Don't want a radon-filled basement. Thankfully, it's not that big of an issue in this part of the country, but in the New England where people have basements, if the radon level can be high enough where I wouldn't want to live in a basement potentially. So that's like the one background radiation thing that you should be concerned with. And it represents thousands and thousands of times more dose than a nuclear reactor 10 miles away. So, any questions before we move on to, yes?
So then how much,
What are you
I
doing?
guess I was curious about the rates that someone might receive from something like chemotherapy.
So for radiation therapy, so if you get like prostate cancer, you need external beam therapy where they take, usually they shoot a beam of very high energy X-rays through you in about, so is there a pin? So if this is your prostate here, they'll shoot beams in several different directions to minimize the dose to everything but your prostate. And in that case, your prostate will be getting about 70 gray. So you can go, wait a minute, that's 20 times that LD5030 that you told me. And the answer is yes, it is. They want to make sure your prostate is dead. But you have to get that 3.5 gray to your whole body. And specifically your rib cage, where you have a lot of red bone marrow, and then also your femurs is where most of it is. So for therapeutic and treatment, the radiation doses are very, very high. And
It's so concentrated
they're so concentrated, correct.
that that's why they're able to, that's why they're effective.
Yes, correct. You want to make sure that every last basically cancer cell is killed. So you have to keep doing that LD50 over and over and over and over again. Say, okay, because think how many cells are in a single prostate. It's billions.
So that's how it's able to defeat or beat cancer as opposed to create it.
Yes.
Right.
And there is some very small risk associated with generating secondary cancers, but it's rare, and that's a problem down the road. You have prostate cancer right now. Yeah, exactly. So no, but that debate does go back and forth. The legislature in California, because they'll be the first to do it, because it's California, is looking into things like that. How many secondary cancers are generated? Because it's a little bit of a conflict of interest. Because no one in a hospital hesitates to give you a CAT scan over and over and over again because they say, I'm the physician. They all have really big egos for the most part. And there's a benefit to it, and the hospital bills it out. So they want to keep those machines running all the time, and it's not that they're trying to give you more dose than you need or there's no benefit to it. It's that it's really that argument. It doesn't have a lot of credence right now that, wait a minute, I don't want 10 CAT scans when 2 is 90% as good. But it could change down the road. The only time that they're really concerned is if you're pregnant, especially early in the pregnancy. If you do not want to get a chest X-ray if they think there's something really wrong with you and you're pregnant. It's a good idea. I mean, not really allowed to give an opinion on that, but it's between your physician and the patient being treated. A CAT scan, don't get a CAT scan if you're pregnant. It's way too much dose. Or cancer treatment, but. Okay, any more questions before we talk about the reactor a little bit?
Is the alpha particle or beta particles can be used for the same reason?
Yes, so that's called, typically it's called radioimmunotherapy, and they'll attach one of these isotopes to a drug that has high specificity for the cancer cell. So it's sort of like attaching because the chemotherapy molecules, whatever it is, also target those cells. If they can find a molecule that binds very strongly to them that has this radioactive particle on it, then they can do that. There's a lot of research being done on an isotope called astatine-211, which is an alpha particle, and that it'll deposit a huge amount of radiation. So if you can get all of the molecules that have astatine-211 to go to a cancerous organ, the range of that alpha particle is like the thickness of a sheet of paper. So none of the areas around it will be affected. So there's a lot of interest in things like that. Beta particles will kind of bleed out into the surrounding area a little bit, but so yes, there's quite a bit of research.
Alpha radiation is safe.
It's safer, but the problem is that if it has any specificity for any of the surrounding areas, then you're going to dose them as well. So you wanted to dose the surrounding areas less than this external beam method is the idea. So There's technical issues with making the radioactive material. The real difficulty is finding molecules that will only go to that cancer that have very high specificity. So that's very challenging. It's a biochemical. I just try to make the stuff, and I leave the biochemistry to the biochemistry folks. Okay, any other questions? Okay, so that's the McClellan Nuclear Research Center. There was a big sign out front until September 10th, 2001, and then we took the nuclear sign down. But the reactor is inside that building. September 10th, yeah. So
2001?
yeah,
Right before?
yeah.
Okay.
Well, I mean, we took it down. That was the last time it was up for the whole day.
Sure, coincidental.
No, that was the last time it was up for the whole day, excuse me. And then, yeah, later that next day we took it down. So this is what a nuclear reactor looks like. So this is a big commercial reactor while they're refueling it. That reactor is called the ATR, and it's I think it's almost it's the country's biggest research reactor. So this reactor is a commercial reactor, it produces about 3 billion watts of power. ATR next to it makes about 250 million watts. And then that little reactor is pretty much the one that we have down the street. And we produce 2 million watts when we're operating at full power. So a big commercial reactor is thousands and thousands of times bigger than our little reactor. Okay, so how does the nuclear chain reaction work? In its simplest terms possible, our fuel is uranium-235. When that uranium-235 absorbs a neutron, it typically undergoes fission. It can go absorption and become uranium-236 and not fission, but the fission process is the most common thing that happens about 80% of the time. When the fission occurs, you get, on average, 2.4 neutrons coming out of that fission, and you get 2 lighter elements coming out. So sometimes 2 neutrons will be produced, sometimes 3 neutrons. And the chain reaction is sustained if you can get one of those 2.4 neutrons to induce another fission in another uranium-235. So you have to play around with how big the reactor is, how much uranium-235 you have, how much control rod material do you have to control the reaction, how much water, which slows the neutrons down. The slower the neutrons are, the more easily they're absorbed in uranium-235 to introduce fission. So it's sort of a balancing act between all of those things to get a nuclear reactor. This is called K. So K is the change in number of neutrons per generation. So this would be first generation. This would be the second generation. This would be the third generation. So you can see there's 1 neutron, then there's 3, and then there's 6 over there. So when you have K equals 1, that means exactly 1 neutron induces a fission in the next generation. So what do you think that looks like? If you're staring at the reactor, what does that look like from minute to minute? Is the reactor changing at all? No, it looks the same. That's called criticality. So whenever the reactor is perfectly critical, it just means we're at the same power. We can be critical at 50 watts, we can be critical at 1,000,000 watts. So whenever you hear in action movies or something like that, like, oh my God, the reactor's about to go critical, our reactor is designed to be critical all the time. You want the reactor, it's not a reactor if it doesn't go critical. So if K is less than 1, it's called your subcritical, and that just means that the reactor is reducing in power, or usually that's shutting down. So we can reduce power without shutting down, we can reduce power and shut down. If K is greater than 1, it's called being supercritical. And that sounds a little more dangerous, but it's not. All that means is you're going up in power. To go from 0, reactor off, to up to 1,000,000 watts, you have to go supercritical. So that in and of itself is not dangerous either. If you go prompt supercritical, that means the reactor is going critical very, very, very fast in the order of milliseconds. That, for most reactors, is extraordinarily bad. For our reactor, it can actually do it based on the physics. Okay, so the facility, it's run by UC Davis. It's 25 miles from the UC Davis campus, or 3.5 miles from this campus. We operate at 2 megawatts. We're tied for, there's 2 research reactors run by universities that are higher power in the country, Missouri and MIT. We're tied for bronze medal position with 2 other reactors that are 2 megawatts. Up until last Wednesday, so 1 week ago, we became not the newest reactor in the United States to reach design power. So a nuclear power reactor in Tennessee reached their design power. They're not hooked up to the grid yet, but we no longer have the newest reactor in the country. But second newest, it's not bad. We'll probably hold we held that title for 25 years, and that record will probably remain for several hundred years. So the reactor, it's called a TRIGA. It stands for Training Research Isotopes, produced by General Atomics. They now make most of their money building Predator drones because it's like 1,000 times more profitable than building small nuclear reactors for universities. And what makes this reactor so special is the reactor is basically the fuel. Any reactor you go to, the reactor and the fuel are almost interchangeably the same thing. So our fuel is zirconium hydride. It's 20% enriched uranium-235, so most commercial reactors are only 5% enriched or 20% enriched. And we have what's called a large negative temperature coefficient. So what that means is as we go up in power, the reactor fights you and tries to level that power off. So when we start up, if we were to just pull the control rods out really quickly, we would see reactor power would do that. So this would be power, and this is time. And that's what you want, right? So someone just pulls all the control rods out, it's not going to run away from you. So we have a large prompt negative temperature coefficient. What that prompt negative temperature coefficient lets us do is we can actually go prompt supercritical, which the reactor will actually go up to about 300 megawatts, make this huge bright flash, and it what's called pulses the reactor. We can go to 350 million watts for about 20 milliseconds. So it's kind of the same physics going on as the initiation of a nuclear blast. But the reactor just shuts itself off because it instantly raises fuel temperature, reactor reactivity goes down, goes subcritical, and shuts itself off automatically. It's pure physics that does it. There's no intervening or anything like that. So all the commercial reactors in this country, by law, have always had to have negative temperature coefficients. So that's based on the fact that they're cooled by water. Does anyone ever can think of a reactor that maybe didn't have a negative temperature coefficient, maybe had a positive one? Yeah, so Chernobyl. So basically it's there. If you pulled out a bunch of control rods and it go up in temperature, you'd get that. So it's a good design to do what the Russians were trying to do, but not a really good safety design, because if you can't put the control rods back in, you can have a runaway reaction. This was not the case at 3 Mile Island. This was not the case at Fukushima. What got them in trouble was the decay heat of the fuel, and that once you shut the reactor down, all reactors like this go from 100% power down to 7% power. So it's not like turning a stove off. The stove is still hot, but it's not producing any energy. When the reactor is shut off, it's still producing 70% of its energy. Right when you shut down, and a day later, it's still producing 1% of its energy. So it's this exponential decay. So if you can't remove that decay heat, so for us, we go from 1 million watts, it's still producing 70,000 watts the second we turn the reactor off. And if you can't remove that decay heat at a big reactor that's, I don't know, the core's maybe a third of the size of this room, versus my reactor is the size of, not quite this geometry, but this is the size of the McClellan reactor. Our reactor can't melt down, because even if we lost all of the water, air just circulating would be enough to cool the core down. So we physically can't have Chernobyl, and we physically can't have 3 Mile Island or Fukushima at this style of reactor. And that's why they're built at universities. So it's physically impossible. Yes?
And how many watts was your guys' producing?
We normally run at 1 million, but we're licensed to go up to 2 million watts. So it's about the same output as a locomotive running at full steam, or full throttle. I'll try not to cough right into the microphone. Any other questions? Okay, you can always ask me afterwards if you're feeling shy. So that is our reactor. So the core is just the very middle structure with all the holes in it, and that's where the fuel elements slide into. I should have brought we have dummy fuel elements, but if you come and visit, I'll show you those. So it's about this big around. The control rods are all the tubes that you see going into it. Those are the control rod connection rods. We have material that very strongly absorbs neutrons. So if you want to make the reactor go subcritical, you just put those in. When we start up in the morning, we basically go in the control room while we're drinking coffee and talking about football and pull the rods out. They travel about, total travel is 15 inches. We pull them out 8 inches to go to 50 watts. And we can maintain 50 watts of power for, I think I did the math, like 50,000 years. That's how much fuel we have. And then to go up to 1 megawatt, we just have to withdraw those control rods from 8 inches, 1 more inch each. So that's the only change, physical change in the reactor that we make, is withdrawing those out 1 more inch, and we go from 50 watts to 1 billion watts. Then past that, if you withdrew the control rods out all the way, that negative temperature coefficient would kick in so much that we actually wouldn't reach our maximum power, or you wouldn't reach the power necessary to damage the fuel. So very, very safe design. So that's the reactor off. This is the reactor on. So you get this brilliant blue Cherenkov radiation coming off of it. And it's pretty cool. So nag your professors to take you out to the facility. We can do a fun lab and talk in a little more detail is the goal. So that's what the actual core structure looks like. The pink elements are slightly more uranium in them, same enrichment, but just more mass of uranium. The black ones are graphite dummy elements. We don't have any replacement fuel for the reactor right now. So whenever we take a fuel element out of service, we move one of the outside ones in and then put a graphite element because it's more efficient than having it just empty water. Any questions about the core structure? So why is it a circle like this? Or a cylinder, excuse me. So why do we want them as close together as possible? Yeah, it makes it easier to sustain the reaction. So if you had more water in between, if you had more aluminum or stainless steel, it's just more things for the neutrons to get absorbed in. You want them to be absorbed in the other uranium-235 atoms. So that's why all the reactors are very, very compact, and all the fuel is very close together. And you have just as much water as you need to cool everything sufficiently.
Do you use multiple banks or just one whole bank?
Just one. So we have 6 rods total. One is called a transient rod, and that's what we can eject out of the core with compressed nitrogen gas to get greater than $1 positive reactivity insertion to make it go prompt supercritical. The other ones are all identical. They're fuel followed. And then we can set one of them, well, we set 3 of them to automatic, but we always set one, the reg rod, to automatic. So all the things that you see of like Homer Simpson doing nothing at the control rod, that's basically, when we bring it up to power and we hit automatic and it stays at a megawatt, and we could probably operate like that for a few months before anything happens. The reactor will automatically shut itself down if there's any problems detected. Usually the most common problem is a loss of a certain indication. So we have to have certain indications to run the reactor, like fuel temperature and monitoring the air and all sorts of things. So if we lose any of those indications, the reactor automatically shuts down. That happens about once a year. Doesn't mean anything unsafe was happening. It's just a loss of indication of what's going on in the reactor. So all of those things are spelled out in our license. Yes?
So, what time of, what amount of time do you have to keep it on, shut it down, or a certain
Uh, we
certain
normal.
time limit to that?
Not really. I mean, we normally operate about 30 hours a week. And some days we don't run at all. Other days, like today, we're running 8 hours to do a radiation for the Australian National University. We're radiating some rocks for them very intensely. There's a purpose for it, I assure you. Any other questions?
Are you connected to the grid in any way? Are the power being sent?
No. It's so we have a primary. We have the primary. Primary water. So all that's water. It's actually looking through 23 feet of ultra pure water down to the core. So 7,000 gallons of water. It's pumped to a heat exchanger, and then that heat exchanger goes to a secondary. It's hooked up to a secondary system. Goes to a cooling tower out back. So no. So on a cold winter morning when the atmospheric conditions are right, you get to see what a 1 megawatt cloud behind the building looks like, because it's just this cloud coming up from the cooling tower. So it would make. Basically, we'd have to get relicensed to make power, and we could potentially make it, but it would be very, very expensive. Okay, so the building or the facility was made specifically by the Air Force about 25 years ago to do neutron radiography. So neutron radiography, everyone's familiar with X-rays, right? So X-rays are really good at looking at dense, high Z material surrounded by lower density, lower Z material, so like bones in your arm. Neutrons, when they're taking pictures of things, it doesn't necessarily work like that. So water shows up very, very brightly, where on X-rays it essentially doesn't show up at all. So we're able to look at things like water in metal structures for corrosion purposes. So that's why the U.S. Air Force built it, to look at water seeping into F-111 wings, because they were finding out there's some potential problems like the airplanes crashing. We do neutron activation analysis, which is always a fun lab to do and fun work. So all the rare earth elements, about 60 elements, we can detect down to various levels, parts per million sometimes. Gold is about the easiest one to do. It's the gold standard. It's the easiest and most sensitive one. We can detect down to about 100 parts per trillion of gold in a sample, depending on what the sample is. So we eject it into the reactor, a little sample, eject it right back out, and run it downstairs to put on very sensitive detectors, and we can identify about 60 elements on the periodic table down to parts per million. So that's pretty fun. Isotope production, we make various isotopes for various purposes. It's almost a whole nother lecture in and of itself. And then radiological tolerance testing. So everyone knows that there's a higher radiation field in space, right? Because as the magnetic field goes out, there can be charged particles in it at higher atmosphere. There's no atmosphere to block out some of the other cosmic radiation. So you don't want to send up a $400 million satellite and put it in that radiation field and then have it last 2 hours before the radiation fries the electronics. You don't want that to happen. So instead of, and you don't have time to send stuff up for 20 years to go, did that last 20 years? So what they do is they'll take electronics, put it next to our reactor for like 20 minutes, and then simulate that entire design lifetime of radiation in space. So we get parts that are going to Mars, we get parts that are going to orbit all the time. So that's neutron radiography, what it looks like. So that's neutron radiography of a ficus that someone brought in from their house. So you can see it's all the water that's actually showing up very brightly. So the neutrons interact very strongly with the water. They don't interact strongly with, there's soil in there. It's filled with soil. It doesn't interact very strongly with the soil. It doesn't interact very strongly with the pot. So the pot is very transparent. The soil, you almost don't see at all. Oh, go for it.
I have class starting in 3 minutes.
Okay. Okay, so I got 3 minutes. Okay. So the water shows up very, very brightly. That's the F-111 wing. That's not the blue glow of the reactor. That's just it's just where the lighting looks blue. Okay, last slide. So I'll give my little pitch for nuclear power. I don't think it's a panacea for our power needs. I have solar panels on my house. I love them, but the sun doesn't always shine and the wind doesn't always blow. So that's what one of our fuel rods looks like. So how much gasoline is in 1 megawatt hour? So to give you some equivalence of how much power is in one of these fuel rods. So it takes 28 gallons of gas to make 1 megawatt hour of power. So we operate about 1,200 megawatt hours per year, and our core will last about 20 years. So we don't have to refuel if we have fresh fuel for 20 years. So how much energy is this? So that's a picture of my car. So this ends up being about, our core, which is the size of that garbage can, is equivalent to 30 Olympic-sized swimming pools of gasoline or oil. So the core is about the same size as the little engine in my car, and that's enough for me to drive my Honda Civic around the world 1,000 times before I have to refuel. And in this case, we're only, if you burn a gallon of gas, you're burning all of it. We're only using about 10% of the fuel's energy doing it this way. So it's the power density of the nuclear fuel is literally 1 million times greater than gasoline, or close to 100 million times greater than a battery. Yes?
Just a quick question. Is there any risks for using nuclear power and stuff?
There is, but they basically look at other industries and say, because it's like the airplane industry. If lots of airplanes keep crash, nobody is going to fly anymore. So they're very sensitive to the public perception. So they say, okay, we're going to take the risk of other industries that people don't really worry about and do it 10 or 100 times safer than that. So the nuclear power industry has targeted being, you know, and it's all statistics because you can't, you know, dams don't break that often, but they set these failures and to design the facilities to be 100 times, 10 times safer than Folsom Dam breaking. I mean, you drive by it all the time. You don't ever think of, oh my God, what would happen if Folsom Dam broke? And they set the reactors to be, you know, designed to be safer than that. So there is some small risk associated with it, but Fukushima was a little bit different. You know, they didn't have a history to know that an earthquake of that size was really all that possible and a tsunami of that size.
Okay, I'm going to cut you because there's another class.
Okay.
Let's